This is section 9.4, series. This section goes right along with section 9.3, where we're going to take sequences and sum them together to make series. We're going to look at finite and infinite series, and we're going to look at two special types that are pretty common. So let's start by defining some terminology that will be helpful for this section. So first let's talk about summation notation. So the definition of summation notation is the sum of the terms of a sequence and write the sequence as our list of terms. So we have a sub 1, a sub 2, and so on to a sub n. And it is denoted by, we use a capital sigma for summation, and you see k here, and you also see j, sometimes n. So this definition is showing the summation from k equals 1 to n of a with a subscript of k. So that k is a counter, and it'll count up each term, and it's always a whole number. So we finish the definition, which is read. The sum of a sub k from k equals 1 to n. So that's how you read it. The sum of a sub k from k equals 1 to n. And k is the variable which is called the index of summation. It keeps track of where you are in the sequence or the series now. So k is 5, you're looking at the fifth term. Let's do an example. So this is from page 661, number 1. And the problem says, write the sum using summation notation. So here is what is given. Negative 7 minus 1 plus 5 plus 11 plus, and then so on to plus 53. So we have to figure out what is happening. How do we go from one number to the next? We have to determine what the original sequence pattern was. And then from there, we have to figure out how many terms we had. So let's see. When you look from negative 7 to 1 and then negative 1 to 5, what you see here is a plus 6. That's also a plus 6, and you can see that continues. So what we have is we are adding 6 to each term. So that makes it arithmetic. So we can use the general term for an arithmetic sequence. So we have that a sub n is going to equal negative 7 plus n minus 1 times our change, which is 6. And now we can simplify that, and we get 6n minus 13 Now we have to find n. That's our next job, to find n. We have to figure out 53. What term is that? So what we're going to do is we're going to take our 6n minus 13. We're going to set that equal to 53. And when we solve for n, we get that n is 11. So now we can write our summation. Our summation will look like this. So we're going to start from k equals 1. And now we know our n is 11. And our a sub k is our 6k minus 13. And that's going to be our answer. Okay, next we're going to look at a couple special sequences. They are the arithmetic and geometric, which we worked with in the last section. So there is a theorem of the sum of a finite arithmetic sequence. So I'm going to write that out. So we're going to write our sequence A1, A2, up to AN, be a finite, and by finite we mean it ends. There's a final term. A finite arithmetic sequence oops, I don't know why that's like. There we go. With a common difference d, which is what we use for the common difference. So the sum of the terms of the sequence is this formula. So we have our summation notation. K equals 1 to n of a sub k, and of course that means a1 plus a2 plus dot 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 all the way up to plus an is going to give us this sum. So S equals n times a1 plus an over 2. So you take the first and last term and average them and multiply that by n, the number of terms you have. It can also be written in this form. To use the original formula, we have n over 2 times 2a sub 1 plus n minus 1 times d. So our original form for an arithmetic sequence, general term, is in that one. So either one of those will work to find the sum of a finite arithmetic sequence. So now let's do example. So number 7 on page 664. That problem says to find the sum of the arithmetic sequence. So we know we can use one of those formulas because we're being told it's an arithmetic sequence. With common difference d. Oops, I jumped up to the next part. So here's a sequence: -7, -3, 1, 5, 9, 13. So looking at that sequence, knowing we're looking for a common difference, we can see that d is going to equal 4. And we can count and see that we have n equals 6. So we can use our formula, S equals n times a1 plus a6 over 2. And I can just change that n to a 6 because we know n is 6. So this is going to be 6 times negative 7 plus 13 over 2. So we get 6 times 3, which is 18. We could also, just to show you, we could have used the other formula. So we could use 6 over 2 times 2 times negative 7 plus 6 minus 1, because there's 6 terms for n, times 4. So we'll have 3 times, and in parentheses we have negative 14 plus 20, which will give us 3 times 6, which is 18. So both formulas work, so whichever one you want to use. Okay, next we have another theorem. And this theorem is the theorem of the sum of a finite geometric sequence. So it's going to look a lot like the last one. So we're going to let it to define our sequence, A1, A2, all the way up to AN. Oops, I put a 4 there. I don't know why. Be a finite geometric sequence with a common ratio. And we're only going to put one stipulation on this common ratio, and that is that R cannot equal 1, because if it did, we wouldn't have much of a sequence. Then the sum of the terms of the sequence is, so we have the summation of k equals 1 to n of a sub k, and that's just going to show us that we're adding a1 plus a2 all the way up to ... a sub n, and that is going to equal a1 times 1 minus r to the n power and that's divided by 1 minus r. Okay, so we'll do an example, and that'll be the end of this video, and our second video will deal with infinite series. Okay, so page 664, number 13. Find the sum of the geometric sequence, and we're given this sequence 3, 6, 12, all the way up to 288. So this is like that example for the arithmetic series. What we're going to have to do is figure out, instead of D, figure out our R and how many terms we have. So R is pretty easy to find out. We just have to figure out how we go from one term to the next. And here we can see that R is going to equal 2. And to figure out how many terms we have, what we want to do is, I didn't write that last term right. This is 12,288. So what we want to do is write our general term. So A sub n equals A1 times R to the n minus 1. So our a sub n is going to equal our first term, which is 3 times 2 to the n minus 1. So what we're going to do is we're going to take that and we're going to set it equal to our nth term, and we're going to solve for n. Okay, so we can divide both sides by 3 first. So 2 to the n minus 1 is going to equal 4,096. And then we have to figure out, is that a power of 2? And you can just do that in your calculator. And it turns out it's 2 to the 12th. And so n minus 1 has to equal 12. So n equals 13. So that means we can do our sum now. So S is going to equal A1 times 1 minus R to the n. And we're dividing that by 1 minus R. So S is going to equal our first term, which is 3, times 1 minus 2 to the 13th, all over 1 minus 2. So when we figure this out, I just put that in my calculator, and I got 24,573. Okay, so as I said, in the next video, we'll start talking about infinite series.